Okay, so here we are in quiz number 4. So it says refer to the sample data from pre-employment drug screening. So basically, we have this data down here, and what it says is positive test result, negative test result. The subject uses drugs, or the subject is not a drug user. So what would be helpful to us is to get the totals. So if you add these up, let me see, 44 and 17, what is that? 54, 61, I think. Yeah. And these ones up, what do you get? 30, 41 looks like. Yeah, so there's the total. And same thing, let's do the total sideways, adding these two up, 44 and 14. This will be the total. 44 and 14, adding these up, what's that? 58. And then these two, 17 and 27, 44, I think. Okay. And then the total, if you add these up, be, what's it going to be, 102, I think? Yeah. 102, yeah. All right, 102 is the total of the totals. Okay, so we figured all that out. Now, so what I did there is I just found the totals of everything, just added everything up. Now, the probability of a false positive. Well, let's make sure we understand what this information is saying. These 44 people tested positive, and they are users of drugs. So they tested positive. The test said, yep, they're a drug user, and they really are drug users. These 17, they're under the positive column, right? They're under positives. They tested positive, but they're not really drug users. They got a bum rap. So these 17 right here, the test said they were drug users, and they really are not. These 14 got a negative test result, meaning the test said they're not drug users, but they really are, right there in the top row here. So they escaped the truth there. They escaped the drug test telling the truth anyway. The drug test said negative result, and really they are a drug user, those 14 people. These 27, negative test result, right, they're in this column, and they're not a drug user, so that's the truth. The 27 people, it said they're not, and they really are not a drug user because they're in the bottom row. Okay, so with all that said, and let me get a fresh screen here after I wrote all over that one. Let's put these totals again. What were the totals? 61, 41, so this was 61, 41, and then the totals over here. Were, I don't remember now, 58 and 44. And if you total everything, it's 102. Okay, now, what's their question to me? The probability of a false positive. So positive test result, but it's false, meaning they're not a drug user. It's these 17 people. They got a false positive, didn't they? Those 17 people tested positive, but it's false. It's false because they're not really a drug user. It's a false positive. What's the probability? Now remember, probability always means part over the total. So what's the part? That's the 17. 17 people got a false positive. Out of the total number of people, what's the total right there? That's the 102. It's a total number of people who took the drug test. So if you divide that on your calculator, I'm doing it right now, you'll get 0.16666. Like that. They want you to round to, what does it say, 3 decimal places. So remember how we circle the third place, look 1 to the right. If it's 5 or more, we go up, 0.167. So the answer we're looking for here is 0.167. That's the probability, which is like a 16% or 17%, 16.7% chance. So that means if you take this test, this pre-employment drug screening, 16.7% of the people who took the test got a false positive, meaning it said they tested positive, they said they were a drug user, but it was false. They weren't really, because that's 17 people out of 102 total that took the test, which is 0.167 is the part of that. Okay, now, who would suffer from a false positive? Well, if you read through this, you'll see the person tested would suffer because he or she would be suspected of using drugs when in reality he or she does not use drugs. That's who would suffer for a false positive. Okay, number 2. What are we talking about on number 2? In a survey of consumers aged 12 and older, respondents were asked how many cell phones were in the household. 217 answered none. 291 said 1. 3. So let me write this down. So 217 said none. 291 said 1 cell phone. And 362, said 2. So this is the number of cell phones in the household. What's next? 362. 152 said 3. 67 said 4 plus 4 or more. A survey respondent is selected at random. Find the probability that his or her household has 4 or more. So the probability of 4 or more. So remember, probability is always the part over the total. So if you add, we're always adding up the total. So add these up. If you add up on your calculator these numbers, okay, so we add those up. We get 1089. So that's the total number of people. This is the number of people in the various categories. 1089. And how many are 4 or more cell phones in their household? 67 people. That's the part of the whole group of 1,089 people that have 4 or more cell phones in their house. So if you divide that on your calculator, you get 0.06152, and they want me to round to 3 decimal places, so this is the 3rd place. Look 1 to the right. 5 means you go up. 0.062. That's the probability. Okay, now, is it unlikely? Let's read the rest of the question. Is it so that's the answer here, 0.062. That's the probability, meaning if you grabbed somebody at random out of that crowd, out of that 1,089 people, if you grabbed one person at random, what's the chance, the probability, that it would be a person who has 4 or more cell phones in their household? There's the probability, which is the same as 6.2%. There's a 6.2% chance, or 0.062, that if you grab somebody at random, they'd be somebody with 4 or more cell phones in their household. You don't need to give the percentage answer. I was just saying it if it might be more meaningful for you. All right, next question. It is unlikely for a household to have 4 or more. Is it unlikely for a household to have 4 or more cell phones? Well, unlikely? I don't know exactly what they mean by. Usually for unlikely, we mean 0.05. If you're less than 0.05, then we say that's unlikely. That's really unlikely. I guess I would say really unlikely. If there's less than a 5% chance of something happening, that's really unlikely. So here we go. And what is it? This is more than a 5% chance, right? It's 6.2%. It's more than 0.05. So it's not really unlikely. It's not like crazy. You wouldn't say like, oh my goodness, I ran into someone that has 4 or more cell phones in their house. That could happen. It's not really unlikely. It's not less than a 5% chance. It's a 6.2% chance, 0.062. So our answer is no, because the probability of a respondent with 4 or more cell phones in use is greater than 0.05. Therefore, it's not unlikely. It's not really unlikely. Okay, so on number 3 here, we're supposed to, basically, if you read the words, this is what matters. Identify the sample space for a couple having 4 children. It's kind of like this: boy, 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 girl, boy, girl, boy, boy, girl, girl, all this kind of thing. I have to do this, but that's for 3 kids, right? See, 3 kids, 3 kids, 3 kids, that's for 3 children. They want me to do the same thing for 4 children. So let's do it. So this is question number 3, 4 children. I'm going to write it out as a tree. Might be easier for you to see. So here we go. I'm going to start this way and go boy, followed by boy or girl. This is your first child. And then your second child is a boy or a girl. boy. This is your second child, like a tree. I'm going to just show a big tree here. Then your third child is a boy or a girl. And then finally, your fourth child. Oh, so I should have written back here. I forgot to write that that was the third child. And now for the fourth child. The fourth child. This is the fourth. Bring this down just a smidge here. Fourth child is going to be a boy or a girl. Boy or girl. So each new child is either a boy or a girl. Okay, so now putting it all together, let's follow the paths here. So this is boy, 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 leads to this result. This is boy, 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 girl. Boy, 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 girl. This is boy, boy, whoop, not there. Boy, boy, girl, boy. Boy, boy, girl, boy to get there. How do we get here? Boy, boy, girl, girl. Boy, boy, girl, girl. So I'm just following the tree from left to right. So how do we get to this next spot? Well, boy, girl, boy, boy. Boy, girl, boy, boy. How do you get to this spot? Boy, girl, boy, girl. Boy, girl, boy, girl. How do you get to this spot? Boy, girl, girl, boy. Boy, girl, girl, boy. How do you get to this spot? Boy, girl, girl, girl. Boy, girl, girl, girl. All right. We're halfway through. I'm going to draw a line. We're halfway through now. Let's keep going. So now we're going to follow this path. Girl, we want to get to here, right? That's a boy there. So how do we get there? Girl, boy, boy, boy. So that's girl, boy, boy, boy. To get to that spot, to get to this spot right here, you go girl, boy, boy, girl. Girl, boy, boy, girl. How do you get to this spot? Girl, boy, girl, boy. Girl, boy, girl, boy. How do you get to this spot? Girl, boy, girl, girl. Girl, boy, girl, girl. How do you get to this spot? Girl, girl, boy, boy. Girl, girl, boy, boy. How do you get to this spot? Girl, girl, boy, girl. Girl, girl, boy, girl. How do you get to this spot? Girl, 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 boy. Girl, 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 boy. And finally, how do you get to this spot? Girl, 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 girl. Girl, 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 girl. Whew. Okay, so that is the sample space right here. This is the sample space. So in other words, what they want you to type in on the answer for number 3 is all those things separated by commas. So you want to start with the first one, BB, right here, the 4 B's. So they want you to type in, I'll just put the answer here, 4 B's, comma, the next one. 3 B's and a G. 3 B's and a G, comma, the next one. BBGB. BBGB. Next, I'll just go dot, dot, dot. They just want you to type all of those in one at a time, that whole sample space, that whole list. And now let's answer the final question. So it just says use a comma, list them all. There'll be 16 of them. If you counted, there's 16 of them. Now, right, I'm just counting this. 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14, 15, 16 different results in the sample space. Now coming back here, it says, find the probability of getting 2 girls and 2 boys in any order. So, probability, 2 girls and 2 boys, any order. So what's the probability of getting 2 girls and 2 boys in any order? How do we figure that out? Remember, probability is always the the part you want over the total. So how many of these listings are 2 girls, 2 boys, any order? Let's see if we can figure it out. I'm just looking. Is that 2 girls, 2 boys? No. 2 girls, 2 boys? No. 2 girls, 2 boys? No. This one is 2 girls and 2 boys. Is that one? No. Is that one? Yeah, there's 2 boys and 2 girls, right? Yeah. Is this one 2 girls, 2 boys? Yeah, it is. Is that one? No. Is that one? No. Is this one 2 girls, 2 boys? Yeah. Is this one 2 girls, 2 boys? Yeah. Is that one? No. This one is. Is that one? No. Is that one? No. Is that one? No. So how many came out 2 girls, 2 boys? 1, 2, 3, 4, 5, 6. 6 of them out of the total 16. 6 out of 16. And now if you divide that in your calculator, you'll get 0.375. 0.375. 6 over 16. We got the answer. That's the probability. 0.375. So that's the probability. If a family has 4 kids, they decide to have 4 kids, that's the chance that they're going to have exactly 2 girls and 2 boys. There's a 37.5% chance. A 0.375 is the chance. You can change it to percentage. 37.5%. We don't need to change it to percentage, but that's what it is. So that's the chance of a family that has 4 kids of having 2 girls and 2 boys in any order. Right? We see the 16 different things that can happen when a family has 2 boys, when a family has 4 children. And out of those, 1, 2, 3, 4, 5, 6 of them are 2 boys and 2 girls in any order. So 6 out of 16, divide it, 0.375. That's the probability that a family having 4 kids will have 2 boys and 2 girls in any order. All right. Right on number 4. It says, use the data in the following table, which lists drive-through order accuracy at popular fast food chains. Assuming the orders randomly, da-da-da. Okay, so drive-through A, the order is accurate 333 times, not accurate 36 times. So drive-through B, accurate, right, the top row is accurate 280 times, not accurate, the bottom row is not accurate 58 times, etc. If one order is selected, find the probability of getting an order from restaurant C or D, or excuse me, an order that is not accurate. Now that's a little tricky. So they're saying a probability, so remember probability always equals part over total. Okay, so probability of getting an order from restaurants C or D or not accurate. C or D. So all of these numbers are from restaurants C or D, right? That's all C or D, or not accurate. So then we would also throw in this group and this group, because although the 36 and the 58 are not from C or D, they're not from restaurant C or D, they are orders that are not accurate. And they said, we're just going to grab an order at random. What's the chance that we get an order? If we just at random grab an order, what's the probability, what's the chance that we're going to get an order that was from C or D, that would be any of these 4, or is just not an accurate order of any kind, that would throw in these 2. So for the part, we have to add all those up. So if we're going to have to add 36 and 58 plus the other 4, these 4. And that's over the total. Does it say what the total is anywhere? I guess not. So you're going to have to add all these things up. Okay, so a lot of calculation here. Okay, I got the total as 1107. And then now I'm going to add up the numbers on the top. Okay, when I added up the numbers in the top, what I got was 494, and the bottom is 1107. If you divide that in your calculator and round, you'll get 0.446. So that's the probability, rounded to 3 decimal places. That's the probability. It comes from that fraction. The top is 494. The bottom is the 1107 number. So we added up. So for the part on the top, I added up all 4 of these and these 2, right? The 36 and 58 and the other 4. For the bottom, I just added everything up. The total was 1107. So that's the probability. If you grab one from this group at random, the chance you're going to get one that's either from restaurant C or D or is a not accurate one, then is 0.446. All right, let's move on. Probability is always part over total. Number 5, use the following results from a test for marijuana use, which is provided by a certain drug testing company. 147 subjects with positive test results, 21 false positives, 158 negative results. Among 158 negative results, there are 5 false negative results. If one of the test subjects is randomized, I have to find the probability that the subject tested negative or did not use marijuana. Hint, construct a table. That's a great hint. Let's do that. So we got to make a table. And what's the table going to be? Well, it's just like the other drug one. You know, back over here, let me go back. Where was it? This one, right? Positive, negative, user, not a user. Let's go do that. So, positive test result. Positive test result. Negative test result. And user, not a user, right? And then we have totals on the right side and the bottom. So it's the same kind of table. All right, let's read the question carefully. 147 subjects with a positive test result. That's the total down here. You see, that's the total number of positive test results, right? Among those 147, 21 were false positive. That means 21 were not users. That's false positive, right? They tested positive, 147 people, 21 falsely so. They were not users, really. You see that? 147 people tested positive, but 21 were false positive, meaning they're not really a user. It's a false positive test result. How do we find the number here? We got to subtract, huh? Right there is going to be 147 minus 21, right? If you do that in your calculator, you get 126, right? Because 126 were actual users, 21 were not users. That adds up to be the 147. This is all the people that tested positive. That adds up to be 147 that tested positive. Does that make sense? Now, over in the right side, now what we're going to do is we're going to say, okay, now among, what is it? Let's see here. Among 158 negative test results, so it goes down here, 158 negative, 5 false negative. Now, what's a false negative? If you test negative, but it's a false negative. Like negative means, if you test negative, the test is saying you're not a user, right? That's what a negative test result means. You're not a user. You tested negative, no drug use. But it's false, which means you really are a user. So that goes here, doesn't it? They really are users, even though the test result became negative. They fooled the test somehow, right? They got a negative test result, but they're really a user. False negative. And then how do we get the one in that box right there? Subtraction again, right? 158 minus 5. This has got to be 153, because then these add up. 5 and 153 add up to be the 158 total negative test results. All right, we got that whole table. Now, oh, and we need to get the total totals. Let me try to do that. Let me get this out of the way. So if I get the totals over here, 126, I'm going to add sideways, and this will be 131, right? I just added these two numbers right here. Right, 126 and 5. Then add these two. 21 and 153 is 174. And then total those. I don't know. 305, I think. Right? Yeah. Right. Yeah, 305. 305 total people in this test. That's the total number of people that are involved in this test they're talking about. All right. Here comes the probability that a randomly selected subject tested negative. So remember how you do probability now. Probability, let me kind of running out of room here. Let me put it over here. Probability is part over the total. We already know the total on the bottom. That's the 305 people total. What's the part? Well, whatever they say it is. What do they want? People that tested negative or did not use. Tested negative or did not use. Okay, well, just looking at, not looking at the totals, just looking at the four inside numbers. How many people tested negative? These people and these people all tested negative, or did not use. Who else was not a user? These guys. So we're talking about this group, and this group. Those are the three groups that either tested negative, right? Both these groups tested negative, or were not a user. These people were not users, even though they tested positive. So it's the 5 plus the 153. Oops, kind of running out of room here. 5 plus the 153 plus the 21. Right? So let's see what we get here on your calculator. 179 over 305, I think. Yeah, and then just divide in your calculator. 179 over 305. I'm getting 0.586. 0.5, oh, and then you round it. It'd be 0.587. 0.587. Rounded to three places. That's the probability that so out of this crowd, if you grab somebody at random, the chance you're going to get somebody that tested negative or was not a user is 58, almost 59% chance, 0.587. Okay, now, where are we at? We're looking at question number 6, last one. So among 9420 cases of heart pacemaker malfunction, 396 were found to be caused by firmware, which is software programmed into the device. If the firmware is tested in 3 different pacemakers randomly selected from the batch of 9420, and the entire batch is accepted if there are no failures, what is the probability that the firmware in the entire batch will be accepted? Okay, let's think carefully about this question, for it's a pretty tricky one. So they're asking us the probability that the firmware in the entire batch will be accepted. So the probability that it's accepted. Well, how's it accepted? Well, it says the entire batch is accepted if there are no failures. No failures in what? 3 different pacemakers are randomly selected from this batch. And the entire batch is accepted if there are no failures. So accepted means 3 no failures. That's what they're saying, right? They're going to grab 3 different pacemakers randomly, and the entire batch is accepted if there are no failures. That's how firmware is tested. They're going to test 3 of them. They have this entire batch. So here's their plan. This is basically how companies do a quality control. Like they can't look at every single thing they produce on a giant assembly line. It's too expensive to pay employees to pull every single thing off and look at it. So what they usually do is they have some plan. We're going to just look at a few of them, and they use statistics. They use probability to figure out, what's the chance that that a bad one's going to get by, or what's the chance that this is going to work well. So that's what we're doing here. We're saying, okay, they have 9,420 of these pacemakers that malfunctions. These are all ones that malfunctioned. 396 of them malfunctioned because of the firmware, which is the software programmed into the device. So in their testing, suppose they were testing these 9,420 pacemakers on their assembly line. And their game plan for testing is they grab 3 of them at random. So out of the 9,420, they grab 3 at random and they test it. And if 3 in a row have no failures, they assume that the whole batch is good and they accept it. That's what it says, right? The entire batch is accepted if there are no failures. What? In the 3 different pacemakers, randomly selected and tested, right? So they grab 3 at random, test them. If there's 3 in a row that are good, 3 no failures, meaning 3 good, right? No failure means good. They work well. You test 3 in a row and there's 3 no failures. They don't fail. They're good. Then you accept the whole batch. Well, what's the probability of that? That would be crazy, wouldn't it? We would not want them to accept the whole batch because we know that this is a bad batch. It's got 396 bad, pacemakers that are bad because of their firmware. So we're just testing the firmware, not other things. So we don't want that to happen. What's the chance that would happen? What's the chance that this whole batch is going to be accepted with this kind of quality control plan? Test 3. If all 3 good, then accept the whole batch. That's the plan. Is that a good plan? Well, how we know if that's a good plan is we see, well, what's the probability that they're going to end up accepting all these, right? Because we know we have some bad ones here. We know we have 396 that were bad because of firmware. So what's the chance of 3 goods in a row? Well, what's the probability, if you're going to grab, what's the probability of getting 1 good one out of this batch? Well, remember how we do probability. It's out of the total. It's the part out of the total. The part that what? The part in this case that's good. Right? That's going to be the probability of 1 good one. So the part that's good out of the total. What part are good? Well, what's the total? Let's start with the total. 9,420. That's the total number of pacemakers that malfunctioned, and we want to know, well, how many of them malfunctioned? It wasn't because of the firmware. We're just testing firmware right now. So what's the part of that whole batch that are good, at least good concerning firmware? We know they're all bad. They all malfunctioned, but some did because of firmware. Some did because of something else. So out of the 9,420, 396 of them their failure was caused by firmware. So what part was good, meaning not a firmware problem? Well, that would have to be the total minus the 396, wouldn't it? Because 396 had bad firmware, and 9,420 is the total number. So if you subtract the ones that are the bad firmware, subtract that on the top there, and what do you get? You get 9,024 that have good firmware over 9,420 total, right? Because there was 9,420 total, 396 had bad firmware. Subtract that, you get 9,024 that have good firmware, add in 9,420 total pacemakers. So divide that in your calculator, and you get 0.9579617. I'll stop there. No, that's not my final answer. Careful, that's not our final answer yet. Why not? That's the probability of 1 good. Right? That's just 1 pacemaker. That's the probability that you're going to grab 1 at random and it's going to be good. Because there's 24 good ones out of 9,420 total. So there's a pretty good chance, 95% or 96% chance if you're going to grab 1 at random, you're going to get one that has good firmware, because most of them do. Okay, but they asked me, what's the chance that you're going to get 3 in a row that are good? Probability that you get 3 in a row that have good firmware. Well, how do you get 3 in a row that are good? You get 1 good one and a second good one and a third good one, don't you? You got to get 3 good ones in a row. Well, what's the chance of that? Well, every single time it says 0.9579617. So you just take that 0.9579617, and means times. And then you do it again, 0.9579617, and means times 0.9579617. Multiply those three together, and you'll get 0.879, rounded to 3 decimal places. That's the answer. 0.879 is a probability of getting 3 good ones in a row. So the moral of this story, what you want to check out, is and means multiply. And is multiply. Whenever you do something in probability, and you want like one good one and the next good one and the third good one, that means you multiply. This is times. You multiply those together. Whereas back over here, notice we had a bunch of ors. Let me give you one of these right here. That's what this section's about. And or and the difference. See back here on number 4, we wanted restaurant C or D or not accurate. We add those up. Or means add. So or means add, because you add them up. You can have these ones or these ones or these ones, right? But and means multiply, because you want something to happen and something to happen and something to happen. You want all those to happen together. For and, you've got to multiply those probabilities together. So that's different than the last few problems, which had or in them. So for or, we add. For and, we multiply. If you can read that writing. I'm getting kind of scribbly there. So for or, we add. For and, we multiply. So right, because they didn't say you want one good one, or if the second one's good, or maybe if the third one. They didn't say or. So they want the first one good, and the second one good, and the third one. They just said they wanted 3 good in a row, which means and. So you multiply those together. And this procedure is 0.879. So it's likely, isn't it? Likely to result in the entire batch being accepted, right? Because that's a 8.8. That's 87% chance. That's pretty likely. This procedure is likely to result in the entire batch being accepted. That's not a good thing, since we know the batch should not be accepted. It's got some problems. So there we go.